Hello everyone. So we're going to move into the your unit 3, section number 1. So now under this section, we are planning to discuss about another conserved quantity. So far we discussed about the conservation of energy in your last section. So we know that by using conservation energy, we were able to solve exactly the same problem that we solved by using kinematics, but it is a easier way because energy is a scalar quantity. So now, similar to that, we have many other quantities that we can say conserved in your physics class. So one of them will be momentum. So momentum will be a conserved quantity that we're going to discuss in this section, at least for the linear momentum. That means we are going to talk about the object that is still moving in translational motion, projectile or translational motion, but not doing the rotation yet. Okay. So now, in addition to that, in physics classes, and you go to the physics 2, you're going to learn about the charge conservation. And later on in advanced level physics classes, there are many other conserved quantities that we are discussing. But in this section, we are planning to do basically conservation of momentum. Right. So conservation of momentum will be very easy to use, but it is still a vector that we're going to discuss. Because of that, you need to use the vector addition informations to solve those kind of problems. So now let's try to share the windows first. Okay, so now what are the chapter numbers? So in your textbook, unit 3, we're going to talk about chapter 8. Okay, chapter 8 is the part that we're going to cover today. Okay, so now let's focus into the presentation. So we're going to talk about linear momentum, and also I will jump into the center of mass, because center of mass is another important quantity, because all the time when you use the object, that we draw the free-body diagram by choosing the center of the object. That center of the object is not actually the center of mass point of the object. It's depend on how the mass distributed throughout the object, right? Because of that, we need to compare, or we need to find the way to calculate the center of mass, at least to some extent in your class. Simple example, if I have two masses here and here, so what is the center of mass of this system? That system center of mass is not in this one, not in this one. It should be in between. If this one is heavier, then your center of mass will be closer to this object. Right? So that kind of things we're going to discuss at the end of this section. Okay, let's first move into the momentum. So how momentum going to be relate to the our known physical parameters like force and velocity and acceleration? How the momentum going to relate with those parameters, right? So now momentum is actually, we call it as the property of moving matter. Property of moving matter, we call it as the momentum, right? So momentum will be able to calculate. We use the symbol lowercase p for the momentum. It is a vector quantity, and it is defined as the mass time velocity. Why p is a vector? Because velocity is a vector, although mass is a scalar quantity. So now momentum, lowercase p, defined as the mass time velocity. Now take the units in here. Mass is in kilograms, is a unit, and velocity will be meters per second. This unit is the unit for the momentum. So we're going to relate that unit into Newton second in a minute, but that is the SI unit that we can use for the momentum. So now how this momentum is related to your Newton's second law, how it will related to force, right? So if there is a mass, if that object moving with velocity v, this object has the momentum. So now how do we going to relate that? So to the force. So now force equal mass time acceleration according to Newton's second law. And then acceleration, we know that we can write it as change of rate of velocity. Now if I take the mass and velocity together and take the change symbol to outside, this part I have it in here is P. So what that means is F net, I will be able to rewrite delta P over delta T. So what is the delta P is? Change of momentum, and then F we can define it as change of rate of momentum. So that is again a Newton's second law representing in by using momentum, not by using the acceleration. Okay, that means your acceleration, velocity, momentum, these all things are combined together or related each other. Okay, so now by watching this, actually I will be able to get the another unit, because you see that change of momentum, we know that change of something, always we can write it as the momentum at final point minus momentum at initial point. If it is the momentum, if it is the kinetic energy, that will be kinetic energy final minus kinetic energy initial. That was the change of something means. So now delta phi has the unit of P basically. This has the same unit. Change of something has the same unit as something, right? So because of that, your force, you can see it in here. I'm going to write that in here. You can see your delta P will be able to rewrite by using force times delta T. We're going to learn this later as the impulse, but at this point, I want you to think the units again, because force will be newtons and change of time is second. What that means is Newton second is exactly same unit as I have wrote it in here, because both are units of momentum. Yeah. So now we related this everything. So now we're going to discuss how to calculate this momentum, right? So now first we're going to think how we're going to do these P calculations before moving further for this discussion. So we'll say I have a object in here. So A and B. I have a ball here, B, and here's the ball A. So now I'm going to push these two balls with some velocity. So this one I'm going to push it by 3 meters per second. This one I'm going to move 1 meters by second, right? So 3 meters by second, 1 meters by second, right? So now when I move these two objects, so A and B should have a momentum because there is a mass and there is a velocity. So listen to the announcement that when we talk about the players, football players, basketball players, whatever that player, the announcement always talking about momentum of the player, because mass and velocity together is important quantity at that place, right? So now A and B objects are there. They are moving with different velocity. They have the same exact mass, but they have different momentum. Why? Because they have different velocity. So now if I calculate the momentum of the A object, mass of A object times velocity of A object, in this case, mass is 1, velocity is 1, then my momentum will be 1 kilograms meters per second or 1 Newton second, right? So now B object, we have 1 kilogram and 3. So then B object also, you can calculate it, and then your answer will be 3 newtons second or 3 kilograms meters per second. That is the momentum of A and B object separately momentum. So now if you need to calculate the momentum of the system of both objects, what you have to do? Then you need to use the superposition principle to calculate it. Momentum of this object plus momentum of this object. If they are moving in the same direction, if one is going backward direction, then you need to think about the directions. One of them will be negative. Okay. So now let's move into the conservation of momentum. So now conservation of momentum, basically in the meaning similar to the energy conservation, momentum conservation is saying that You cannot create the momentum or you cannot destroy the momentum if it is an isolated system that you do nothing during the collision of these two objects. What that means is if two objects going to be collide just by coming with some velocities, if you do something, some external force at this point, then that momentum conservation not going to work. That's what it means. So your net force, external force, should be 0 during the collision. You should not do any external force when they will hit together and repel or attract together or move, right? So now what will happen? So we're going to discuss about the things happening before the collision and after the collision. So we're going to ignore this part right now. So we are calling what is happening the before collision, what is happening after collision. Then you're going to write initial momentum for whole system is equal final momentum for whole system, right? What will happen is if I have A and B object, they're going to come with some velocity, they're going to hit. After they hit, they decide which direction they will travel according to those initial velocities and according to the masses. They're going to decide and travel maybe both in this way, maybe both in this way, maybe this way, or maybe one is this way, one is other way, right? So that's possibilities come in because of different masses of the object and the initial velocities of these objects. But what the thing that we're going to discuss is momentum, that if you write just before the collision and after the collision are equal to each other. That's what the momentum conservation means. Okay, so what that means is you're going to write before momentum, we'll say PI or initial or before, whatever you think you can write, but I will use the initial and final. And momentum after we call it as P final. But it's very important that you do the problem with your coordinate system or by choosing your axis according to the problem, XY coordinate system. Okay, because it is a vector quantity that we're going to discuss. Okay, so now conservation of momentum give us some informations of the your collision, right? What direction they will move and those things. But we're going to move into the collision now. Collision can be defined as elastic and inelastic. So elastic and inelastic definition coming from not because of the conservation of momentum, it is coming because of the kinetic energy conservation. What that means is if you have two objects collide each other and if you calculate the energy, especially the kinetic energy, we're going to do everything on the horizontal plane. If you calculate the kinetic energy of the system before the collision, equal to the kinetic energy of the system after the collision, then we call it as kinetic energy conserved, as we discussed earlier section. And that case, we call it as the collision is elastic collision. So kinetic energy conserved when the collision is elastic. How do you define elastic collision? You need to definitely calculate the kinetic energy initial, kinetic energy final, and take the difference between these two. If there is a value after you take the difference between these two, that means it is not elastic. Okay, so what that means in here, kinetic energy initial should be equal to the kinetic energy final. In other way, change of kinetic energy should be equal to 0, then your collision will be elastic. That's the definition of elastic collision. Okay, but there are inelastic collision. In inelastic collision, definition is kinetic energy is not conserved. That means if you calculate the change of kinetic energy or kinetic energy initial, final minus initial will not equal to 0. That's the only way that you can say collision is elastic or inelastic. So does the conservation work in both collision? Yes. So conservation of momentum is working for elastic and also inelastic. Only the kinetic energy conservation breakdown for the inelastic collision. Okay, so now let's move into the conservation of momentum. As I mentioned, in isolated system, if there is no external force, then momentum will be conserved. That means initial momentum before collision momentum should be equal to the after the collision momentum. Okay. So now I know that in your class we probably not doing much about the two-dimensional and three-dimensional collision, but at least to get an idea, if your collisions will not be always one-dimensional. That means if these objects collide each other, these are not in always one-dimensional. This object may decide to go in this direction. This object will decide to go in this direction. That means that will be a two-dimensional problem, right? But is still your momentum conservation valid? What you have to do is you just use your XY coordinate system and write the momentum initial equal final for X direction and write the momentum, your Y momentum initial equal to the Y momentum final, then you will be able to find whatever unknown velocity or the angle that they will travel. And simple example is here that I have a M2 ball at rest. This is staying at rest. So my M1 come and hit. Then M2 decide to move in this direction. This is M1 and M2 decide to move in this direction, right? So now this is not one dimensional. This is X, Y, and both directions. So now it is better that you label your X and Y directions that we have Y direction this way and X direction this way, and then you write the X directional momentum. So now when you write the X directional momentum, your initial is X directional, that will be M1 times V1 initial, but your final momentum from M1 will be M1 V1, right, final times this angle, because you need the adjacent of that, so that will be cosine of theta, and but M2 will be 2 final times adjacent of this one will be cosine of theta 2. So that will be your X direction. Then you do it for the Y direction. When you do it for the Y direction, this does not have initial momentum towards Y direction. That means it is 0. But Y direction, you have your M2 has the positive value, but M1 has the negative value because this is negative Y direction. Okay. So the energy conservation will be easier to use, as we know. That's the only the difference. Other than that, you are solving the exactly same way of the problem. Okay. So now let's move into the impulse little bit. So now we talk about the momentum. So we talk about the momentum relation to the force. That means change of rate of momentum is equal to the force. That's the Newton second law, new version of the Newton second law. So now when two objects actually hit each other, there is a force created at that time interval. These two objects going to be hit each other. When they hit each other, there is a force acting on this object, and also exactly same force going to act on this object, right? Because they are equal and opposite forces according to Newton's third law, right? But this force is how long it's going to stay in there. That force is very, very short time going to be staying there, right? So if I ask you this force and time separately when they hit, think about the you're going to hit the tennis ball in the racket. So can you find the force and time separately for that collision? So that is not possible. Because of that, sometimes we may need to calculate the impulse. Impulse means basically you calculate force and the time together. So force and times together, we call it as impulse. You remember that earlier I mentioned that this is change of momentum according to Newton's second law. But now what is the units of impulse? impulse unit will be exactly same as the change of momentum unit, because this is change of momentum. This will be newtons and seconds, right? Or kilograms meters per second. So that will be exactly same unit as the momentum. Impulse has same unit. So now only thing I want you to think, if you calculate the change of momentum, so you calculate the change of momentum for whole system, then what will happen? Whole system, these two forces are equal and opposite. If I calculate for this both system impulse, there is no impulse, because you have exactly same force, and then your impulse going to be basically hit on this one, going to be cancelled out. But if I ask you to calculate the impulse, that means I basically asking you to calculate the impulse on the one object only. That impulse will be the same for the other object. Okay, so that means you just need to calculate the impulse only for a one object, not the system of object that hitting each other. Individually, you need to calculate them. Okay, so now I don't know, I have time for this. So you guys going to do problems during your recitation session, but I'm going to just initialize the problem. You may have exactly same problem in your recitation, but to get an understanding how to do the things by using momentum conservation. So I have a horizontal layer track and I have two carts, masses are given, right? And then it says first cart is accelerated to initial speed is this one, and then second cart is at rest. When you say rest, that means initial velocity for the second cart is 0. Okay, so now they're going to collide, and other information you need is move together. Move together means basically they have the same velocity. What is happening is you have one object V1. I'm going to probably change the color in here. You have one object, that is my M1 object, right? That is moving in this direction. I'm going to draw the velocity here. V initial of the one object that is given as 5 meters per second. Okay, so now there is a second object which is actually staying at rest. That means V initial for the second object is 0. Now, definitely we know what will happen if I have this object is at rest. If this object come in with some velocity, they're going to hit. And then now it says these two objects are moving together. If it did not say they are moving together, you need to take them separately. But in the question, it says these two objects are going to move together. That means they all have the same velocity. I'm going to say V final for the 1 and 2 both, right? So now this part is your before collision, and this part going to be after collision, right? So now what is our momentum conservation? Before collision momentum is equal after collision momentum, that we're going to write it for the system, not for the individual system. And I'm going to write by choosing the direction, because everything is in X direction, this problem. So, but I'm going to label the Y direction. That means if I measure something in X direction, that will be positive. If something is negative direction, that will be negative. So I'm going to use this equation towards X. That's what it means. Okay, so now we need to write the initial momentum. So now M1 has the velocity that will be, just don't plug the values directly. First write the equation by using your defined variables. So initial 1. So second one, I have initial velocity 0. If something 0, you can just write it as 0. 0 equal, right? And then I have M1 and M2 are going together. So then your mass will be, so that my pen is not writing it correctly, M1 plus M2 together, excuse me. So M1 and M plus together going to move with the velocity V final. Okay, so next step is, question is asking what is the speed of two cars after the collision. That means V final is the solution I need. Find it out with your algebraic equation first. and then plug in the numbers m1 I initial 1 divide by m1 plus m2. Now you have all the information in here. Plug it and calculate the V final. So give the direction of V final. Since you are using in X direction, then your V final will be towards X direction. Okay, so that's the very easy conservation of momentum. And then part B, is it inelastic collision? Why need the mathematical explanation? That means I want you to find change of kinetic energy and show that change of kinetic energy is not equal to 0, then it is inelastic. So you need to prove this. Okay. And then what is the impulse on each other at the collision? So that means you need to calculate the impulse according to the discussion that we had. So you know that I need some space in here, but I'm going to probably move into here. So I need to calculate the impulse of one object. You cannot calculate the impulse for both objects. Impulse will be equal to, as we know, change of momentum. I'm going to do it for the first object. So that means P final for the first object minus P initial for the first object, right? So now final for the first object will be M1V final minus, so that is to the right direction, but my initial also same direction, impulse also a vector. Because of that, make sure that you use the direction. In this case, everything is in X direction. Because of that, I'm not getting double negative or something, right? But if something going downward direction, you need to, backward direction, you need to get it negative. Now P1 initial is M1 V1 initial, right? So you have those numbers, then you plug it and calculate it. That will be the impulse of the each object. That will be exactly same if you do it for the other object too. Okay, so now next step is moving into center of mass. Okay, so center of mass is the basically mass acting point of the your object, or your all the forces acting on the object we have to draw at that point. That is, we call it as the center of mass point. So now center of mass point is the one that who doing the actually translational motion. As an example, if I try to throw this up, this object will basically moving up, not this way. It's going to move, rotate and going up, right? This rotation is happening in different axes that we did not talk about, but this center of mass of the object is the one that do the translational motion. So translational motion is doing by center of mass object. And you can see that in this lady is doing the diving. This is the center of mass point of the body. So that is what they do in the parabolic motion. But this is not the way that usually we do the diving. Diving is body is keep rotating and doing the parabolic motion. Now parabolic motion, you see that this part is still, this dot is staying on parabolic path, but your whole body is keep rotating, right? That is the rotational and translational together. Okay. So now rotational part we're going to discuss later on, but now we're going to move into this center of mass calculation. Okay, so I have another example. If you throw the baseball bat, definitely your center of mass will be closer to the thick end, right? If you take the donut, although you don't have anything in the center of the donut, but your center of the donut will be the center of mass point, right? So those are the points that we going to discuss, and this is the what that we're going to actually calculate. So now if you have two particles, to calculate the center of mass, we'll say this is again important that you use your coordinate system. I mean actually not the direction, but it's otherwise it is a direction, but you need to think the coordinates, like you have 1, 1 coordinate, or you have negative 1, 1 coordinate, that kind of things. Because of that, still you need to label your X and Y correctly and start from wherever the question asking for you to do the center of mass. As example, if I have a MA object staying with XA distance from the origin, and MB object is staying with the XB distance from the origin, that means center of mass that I decided here, I know that it is in between these two, I am measuring with respect to the origin. Okay, because people can give you the question, you have one mass here, one mass here, find the center of mass of this system with respect to this point. That means you need to find the distance from this mass to the center of mass. Somebody can say, find the distance from this mass to the center of mass of the system. Or somebody can say, my origin is here. Can you find the center of mass with respect to the origin, right? That kind of things can happen, right? Now, this is what I'm doing by choosing the origin on the x-axis somewhere, then I'm going to find the center of mass from that point, right? So now it is very simple calculation. So you're going to get mass of each object, take the mass of first object and distance to that object, that will be my MA and XA, and then add MB and distance to that object from exactly same point, MB, XB. And then you're going to divide by the total mass, right? So now, question is, if MB is on the other side, then what you're going to do? In that case, your XB that you are getting will be a negative value that you need to include, okay? Okay, good. So now, that is how we're going to calculate the center of mass. If you have many, many masses, you just keep adding them with the distance. Okay, that will be the same for y-axis, c-axis, x-axis, right? So now this addition, you know that m1, x1, m2, x2, that I can write it as a compressed version by writing summation sign. Summation means basically you are adding I equal 1 to n. What that means is you're going to add m1 x1 plus m2 x2, and you keep adding the terms until you have mn xn. That is your last mass. That is what the summation I equal 1 to n mi xi means. Okay, I think it's a simple thing, but yes, that's the summation notation. Okay, so now that's how we calculate the center of mass. So now this calculation of center of mass in your class, we are doing conceptually, but this is actually calculus kind of calculation later on. If your object is irregular, if you have mass distribution everywhere, then you need to definitely get the calculus to calculate the center of mass by doing integrals. And but if you go to the laboratory, if you need to find the center of mass of your object, we'll say you have a New York map, the structure of the New York map in your classroom, you need to find the center of mass of that object. So now this is the simplest way that we can do. One way is you can keep the map on the kind of like a pivot point that you can basically find the center of mass, right? So that is one way. The other way that we're going to discuss will be basically simple way that you can try to hang the object. We'll say I have this object, right? So you're going to hang this object, right? So like this, right? When I hang it on the wall, you're going to see like this. Then you're going to draw your vertical line on the paper. We'll say this is my vertical line that I hang at this point, right? So now I'm going to hang this in different other point. We'll say this point. Then I hang it. Then it's going to be like that. Then you're going to draw your line exactly vertical to that place, right? So you keep rotating and drawing those lines here, draw the another line here, draw the another line. So these all lines will go through this point. That is what the center of mass point or center of gravity point for that object. If it is irregular, it is a big object, that is the best method that you can calculate the center of mass. So in addition to that, if you need to find the center of mass on meter ruler at your classroom, so you need to find, you will have a kind of like fulcrum that you can keep your ruler, and then you're going to keep it on top of your fulcrum, and then you're going to balance it. So then if you can keep it at the center of mass point, this object going to be balanced, right? So now I have a bird, eagle, that I can balance by using his beak, right? So you see that this object I am balancing with this pivot point, but he's not, his center of mass is not inside the body, his center of mass is on the beak, you see. So because his feathers are heavier than his body, because of that he's going to keep the center of mass point on the beak, right? That is by using the pivot point that I will be able to balance the bird. Okay, so that's another way that you can see the center of mass point. Sorry, so okay, so this is the, you're going to do the problems again in your class. I have basically 3 masses. They are in, I'm not going to solve the problem, but I have M1 mass and I have M2 mass, and it is says sides length are equal, and M1 is here, and M2 is here, and M3 is here. So equilateral angle and length is 140, M1, M2, and M3, and this will be around 140 centimeters. So now where is the center of mass of the system? That's what I said earlier, from the M1. So that means everything you're going to measure, that means basically you're going to select this as your origin, okay, X and Y. That is your origin, that 0, 0 point. After that, you're going to find the center of mass of the object by using your formula. That means this is basically sitting in 140 and 0, and this is going to sit in exactly in the middle, right? That will be 70, and in y-axis I need to find this height, right? So this height you need to find, because these are exactly same size. This will be 60 degrees. That means I have 140 times, calculate it, 140 times sine of 60. Yeah, 140 times sine of 60 will be vertical height. Sine of 60 is √3/2, and 140. So that means basically 70 and √3. So that will be your answer in here, 70 and √3. Right, after you know the coordinates of this one, you're just going to write your X center of mass, right? So equal your M1 object, and distance to M1 object from the origin is 0, and then add M2 object, distance to the M2 from the origin in X-axis is 140 centimeters, and then plus M3 is staying on X-axis as 70. Divide by M1 plus M2 plus M3. So then you have all the numbers, you're going to plug in. And then you're going to do exactly same thing for Y center of mass. So that will be M1 Y coordinate for the M1 plus M2, and Y coordinate for the M2, as we found it is 70√3, and plus M3 times Y coordinate is still 0, divide by M1 plus M2 plus M3. Okay. So it is that simple, but you need to make sure that you know the coordinates of each object sitting on the your question. Okay. Okay, so that's it for this section. So join your recitation session and work on the problems to understand the concepts better.